Now, as I mentioned previously in this chapter, sometimes with elimination reactions, you are going to have to make a choice because you have two beta carbons that aren't in the same chemical environments. And so let's talk a little bit about what that means. When we look at this, we identify our leaving group, and then we look at the carbon that's attached to the leaving group, and that's the alpha carbon. Okay, but in elimination reactions, we're going to move a hydrogen from the beta carbons, which means they're beta hydrogens. And so with this kind of group here and with this group here, you can see that there are some differences. So for example, this carbon is attached to two other carbons and two hydrogens. Well, this carbon is just attached to three hydrogens. Now, what this means is that in the reaction, this hydrogen or proton can be removed, and you would form a double bond between the second and the third carbon. This proton can also be removed, and you would form a double bond between the first and second carbon here. And so what we notice is that when we look at this reaction, it forms both the products, but it forms one in excess. So it forms more of hex-2ene than hex-3ene. And so we call this a regioselective reaction. And I just want to remind you that regioselection, all that means is, or regioselectivity, all that means is it's the preference of a reaction to take place at one site over another site. So all regioselectivity means is there's some preference for where this, there's some preference for which site is going to be involved in the chemical reaction. Now, when we look at this, right, hex-2ene is formed in 68% and hex-1ene is only formed in 16%. And so what you're going to see here is this, the major product is the more highly substituted alkene. And what that means is when we look at this alkene and these double bonds here, there's a hydrogen and an R group. And then of course there's a hydrogen here and an R group. And I've invertedly shown this as cis. It's not cis or trans necessarily. But what I want you to see is that there are two R groups attached to these double bonds. When we come over here to the hex-1ene, we have an R group and we have a hydrogen, but here, my bonds got really wild. Let me back that up. Boop. We don't want any wickedy wild bonds, right? We have two hydrogens. And so when we say it's more substituted, what we're saying here is we have more R groups, right? So hex-2ene has two R groups that are attached to the carbons of the double bond, while hex-1ene only has one R group. So that's what we mean by more substituted. And so the question is, of course, why is hex-2ene the major product and not hex-1ene? Like, what about that additional stabilization, that additional R groups make it more stable? And so when we look at our free energy diagram, what we are going to see here is that, well, first off, what you're looking at is you're looking at a red line, which is hex-1ene, and then you're looking at a blue line, which is hex-2ene. And what you're going to see is that the energy barrier of the reaction for hex-2ene is smaller, right? When deprotonation takes place at that C3 carbon here. So that means it requires less energy. So it's got a more negative delta G. And so it turns out that because it requires less energy, then it's going to be the more stable product. So we can kind of have this wide sweeping idea that the major and let me put it in blue so I can color code it. The major alkene product, which is shown here in blue, of an elimination reaction is the most stable one. Okay. Now, let's talk about alkene stability, right? Because this is something that we can predict. Because of the importance of alkene stability in elimination reactions, we need to know how to evaluate the relative stabilities of alkenes. So this is something that you need to know how to do. And so the relative stabilities are shown here in figure 9.25, and there are really two trends that stand out or should stand out to you. And the first trend is that alkene stability increases with a greater number of alkyl groups attached to the carbon-carbon double bond. And so we say that's an increasing degree of alkyl substitution, right? But notice that this is going to be the most stable here with the 4 alkyl groups, and then this is the least stable here with just 1 alkyl group. The other trend that I want you to notice is that trans, when we are able to see the difference between trans and cis, trans alkenes are more stable than cis alkenes. And this just is because of sterics, right? If you have the 2 big R groups on the different sides here, they're going to be more stable, right? Because they have more room, less steric repulsion. And so let's look at that on the next slide, because there's a great visualization here. And so, as I mentioned, alkene stability is going to increase as alkyl substitution increases. And that's really because of hyperconjugation, which we're going to discuss later here. But it's a little bit easier to see the trans and cis stability. Trans isomers are just going to be more stable than cis isomers because of steric strain. The bulkiness of the 2 alkyl substituents just causes those electrons from those groups to occupy the same space in the cis isomer, and so there's a lot of strain here. And they're on opposite sides of the trans isomer, opposite sides of the double bond, and so repulsion of those electrons just decrease there. And so with this steric repulsion, that increased steric repulsion here decreases the stability of the cis isomer, so it's less stable. Now, previously, we looked at a equation 942, which was looking at an E2 reaction in Regio Selectivity, but we're also going to look at this equation, which is 943 in your book, and I want you to notice here, right, that we have beta hydrogens here and beta hydrogens here, right? And then this is the more, like, we're removing these hydrogens, that gives us the more stable product. It's a more highly substituted alkene product. There are more R groups around the double bond, right? Before this was really understood, Alexander M. Zaccev, who was a Russian chemist who lived from 1841 to 1910, he observed this regioselectivity, and he summarized it kind of based on follows. The major elimination product is the one produced by deprotonating the carbon atom initially attached to the fewest hydrogen atoms. So let me write that for you. The major elimination product is the one produced by deprotonating the carbon atom initially attached to the fewest hydrogen atoms. And so that's what we see here, right? This guy here is only, that carbon's only attached to 2 hydrogen atoms. That carbon has 3 hydrogen atoms. That's the one that's removed. And so that's what he observed. Now we know the reason we observe this is because increased stability. But in 1941 to 1910, that kind of late 1800s, early 1900s, this was the observation that we can make. So Zaccev's summary here from his kind of empirical observations, as I mentioned, is known as Zaccev's rule. And so sometimes the more highly substituted alkene product you'll hear referred to as Zaccev's product. Okay, that's a little bit of an older terminology, but it's one that I just want you to be aware of in case anybody's like, well, that's Zaccev's product. Then you'll know that that's what's going on. Now, there are exceptions, like all rules, there are exceptions to them. And so let's look at some of those exceptions. One noteworthy exception involves strong, bulky bases, right? So our favorite kind of bulky base that we're going to see is this tert butoxide ion. And so remember, it's a really bulky base because when we draw it out, and of course that potassium, there's the spectator ion. That's what it looks like. And so that's a T-butyl group or a tert butoxide group. And so when we look at this, when 2-iodahexane, which is our substrate, is treated with this potassium tert butoxide, the major product here is the 1-hexene. And so that means we've removed the proton from the carbon with the most hydrogens instead of the least hydrogens. And that's just because there's a lot of sterics that go into this, and I'm going to show some of that on the next slide. But basically, there's just not enough room for this big bulky group to get in here, okay? And so a lot of times this is called the anti-Zaccev product. One of the other things I want to point out that you're going to see is a lot of times when you have like a strong, like a base like this, you'll notice that the conjugate acid, particularly if it's an alcohol, is used as the solvent. So that's just something to be aware of. So you'll see that as the solvent there. Now, let's look at this for just a moment here. Actually, I think I want to skip this. This is a slide that I thought I had deleted. And so we're just going to skip that and continue on, and leave basically that as is, but understanding that there's some sterics that are involved. This is talking about molecular orbital theory, and you'll learn that if you go on to physical chemistry. If you'd like to have a longer chat, I'd be happy to talk with you, but I feel like it's really outside the scope of this course. It's labeled as a deeper look in your book, but it's just something that we're going to save for some upper level courses. So, and again, I thought I had deleted that slide and I didn't. Let's talk about intermolecular reactions versus intramolecular reactions. So we generally think of chemical reactions being between two separate species. This is like an intermolecular reaction, right? Which is one between molecules. Okay, where we have this reaction between two molecules, and we've shown a lot of that all throughout organic chemistry. But you can also have a reaction between functional groups that are part of the same molecule. They're just attached to different places on the molecule's backbone. Now, this type of reaction is said to be an intramolecular reaction, and it just happens within the same molecule. And this is one of the ways that we can form rings or sometimes long chains. And so let's look at rings for an example. When we look here, and this is just an example of an intermolecular and an intramolecular reaction. So equation 945 here is going to show you an intramolecular Sn2 reaction. And what's happening here is this O- on one side of the molecule is acting as the nucleophile, and this chlorine is a leaving group. And so these electrons can whip around and attack this carbon and bump off that chlorine. And now you have formed an ether here. This is tetrahydropuran, also known as THP. Okay, and that's the ether that we formed. Now, in the same reaction vessel, you can also have an intermolecular reaction where the electrons on the oxygen attack a different molecule and go here. And then that's kind of what you get there. So whenever an intramolecular reaction can take place, an intermolecular reaction is also possible. And so these two reactions compete with each other. And so, of course, our burning question is, well, if they're competing with each other, which one's going to win and why? Well, experimentally, an intramolecular reaction tends to win out. Okay, so this guy tends to win. When it's forming 5 or 6 membered rings. Right? The formation of those 5 and 6 membered rings is the favorite outcome because of the interplay between entropy change and strain during the formation of a ring. For a ring to form, the two ends here really have to form that new bond, and that's going to really reduce the freedom of movement within the molecule, and that loss of molecular freedom results in a decrease of entropy, right, which is unfavorable. So if we lose molecular freedom, we decrease our entropy, and of course that's unfavorable. Okay, so that's for smaller rings particularly, but as the chain becomes longer, it's just less likely for the ends to meet to form the ring, and so the decrease in entropy becomes more pronounced and the process becomes even more favorable. The other thing that's at play here is ring strain. So remember from chapter 4, ring strain is going to decrease sharply to 0 on going from a 3-membered ring to a 6-membered ring, and larger rings have a small amount of ring strain. So what this means for us is the size of ring being formed increases from 3 to 6 members. The process of forming the ring becomes easier energetically. So those are kind of opposing factors, that entropy and strain. And so it just kind of reaches this optimum, like perfect conditions from 5 and 6 membered rings. Okay, and that's one of the reasons why when you go to biochemistry, you are going to see 5 and 6 membered rings in biochemistry really more predominantly than anything else, particularly when we talk about sugars. Okay, so let's talk about sugars just a little bit here. We saw in the previous topics on biomolecules that monosaccharides are pretty small carbohydrates, and they're often shown in their acyclic form, which is that long ring. In nature, though, carbohydrates mostly exist as these more complex structures like starch and cellulose that just have tons and tons and tons of these guys connected, okay? And I mean, thousands, right? And their ring forms are what are really connected. Now, one of the things that you're going to notice here and what connects these rings, you get something called an acetyl functional group. Now, this is what's going to contain, this is what's going to link these together, is this acetyl functional group. And it's shown in its generic form here. It's characterized by a carbon that's bonded to 2 R groups, But here's the easiest way to identify it, honestly, is it's a carbon that's bonded to two oxygens. When you look at this, there's a lot of carbons that are bonded to one oxygen here, right? But this carbon is special because it's the one that's bonded to two oxygens. And so we a lot of times identify that's an acetyl bond, but that's called an anomeric carbon. And the easiest way to identify that is it's connected to two oxygens in an acetyl bond. Okay, and so the acetyl group involving a sugar can be produced in the laboratory just simply by treating a monosaccharide with alcohol under acidic conditions. So if we have our long chain monosaccharide here, right, and we treat it under acidic conditions, we end up with a alpha D glycoside and a beta D glycoside. So this is glucose. And so what we see here is when we treat it with acidic conditions, then, right, the OH here, right, has been replaced with a CH3 here. Okay, and so these are now called glycosides because here was glucose with the OH, and now we have glycosides here. We do get a mixture of diastereomers. One of the diastereomers is alpha, where this glycoside bond points down here at the anomeric carbon, the one that's attached to two oxygens. And then we can have a beta where it points to the side, or in Haworth projections, it'll point directly up. So the reason, the way I remember this is alpha, that glycosidic bond is going to point down, right? And in beta, that glycosidic bond is going to point up, and that's alpha and down and beta and up. And so the consonants and vowels never go with each other, right? So it's always consonant vowel with how it starts. And that's how I remember it. It's how I still remember it today, right? But it's all about that glycosidic bond. And we identify the glycosidic bond because it's the carbon that's directly bonded to the two oxygens. It's the only one that you're going to see there. And that's really the definition of a sugar. Sugar is going to have that and be able to form that glycosidic bond. Now, to understand why we get a mixture of diastereomers, we can look at the mechanism here. What we see is this takes place by an SN1 mechanism. So in the very first step here, these electrons attack the proton here in a proton transfer reaction, and then we get heterolysis. Now, when we get heterolysis here, where this water group pops off, remember that's an excellent leaving group. Water is very stable, so it's just going to pop on off. What we notice now is we've lost some of our stereochemistry here because we just have 3 bonds, and so that's a flat planar molecule. So the nucleophile can attack above or below the plane of that bond in a coordination reaction. When it attacks below here, you can have a proton transfer, and then now we've got our tetrahedral structure back. So we don't have any rotation or anything along those lines. And it's going to point down below the ring. And then if it attacks above, right, we're going to be out here as equatorial, but we know, of course, above the ring is what we're really looking at. And so the reason that we see these is because it can attack from above or below. Now, in nature, complex carbohydrates consist only of D-glucose subunits, can differ in the way in which the acetyl groups are connecting the sugars together, okay? And so in cellulose here, which makes up about half of wood, I want you to notice that the carbon here, which is our anomeric carbon, that's where we start counting as 1. So this carbon here, right, is attached to the 4th carbon on another sugar unit. And so the anomeric carbon, which is the one that's attached to 2 oxygens, is going to be number 1 when we count. And we talk about that bond. This is an acetyl bond here. And what we see is that it's beta because this is pointing kind of out or up. And then we're connecting the 1,4, and that prime just means that it's another ring, right? And so that's a glycosidic linkage, and that's cellulose here. Now, by contrast, amylose is a complex carbohydrate that consists of about 20% starch, which, like, for example, is shown in corn, okay? And we see that we've got the bonds here are alpha 1,4. So these are pointing down, glycosidic linkages. And then, of course, we can also have amylopectin, which is about 80% of starch. So 20% of starch is amylose, 80% is amylopectin. And what we see here is this is a combination of an alpha 1,4 glycosidic linkage and an alpha 1,6 glycosidic linkage. And so these relatively small differences in these complex carbohydrates can have a large impact on macroscopic behavior. Because look, we don't eat cellulose. We don't go out there and eat wood. We don't do that because our body can't digest it. But we can eat corn, and it's got amylose and amylopectin in it as far as the sugars are concerned. And the reason that we can eat this is because it's got this alpha linkage instead of the beta linkage, okay? Now, maybe the burning question in your heart is, well, okay, why can things like termites eat wood? Well, when termites devour wood, they're after the cellulose, which is this, and they have microbes in their gut that use enzymes to break down the cellulose into smaller sugar units that are easier to digest that we just don't have, right? So we don't have the enzymes that can digest this. Our enzymes can digest that. And so that's why we eat wood and not amylose and amylopectin. Now, equation 949 here shows that a glycoside can undergo acid catalyzed hydrolysis to produce the monosaccharide. The mechanism for this reaction is identical to the one that we shown previously, except the roles of water and methanol are reversed. And what I mean by that is that water is the nucleophile and alcohol is the leaving group. So if we look here, this is a glycoside. We can turn it back into the sugar, glucose. Here, it's just the reverse of that reaction. Well, the stomach, we know our stomach provides an acidic environment. So you might think the breakdown of complex carbohydrates into their monosaccharide subunits would take place in the stomach. But acid hydrolysis is really slow for the body to make use of complex carbohydrates as a quick source of energy. So instead, the hydrolysis depends on enzymes. I get super jazzed out about enzymes. They do all the kind of chemistry in the body. They're really exciting. And so this is a chemical reaction we would do in a test tube, but enzymes are so much more efficient in our body. And so the enzymes that are in the saliva in your small intestine are super highly specialized, and they only target those alpha 1,4 glycidic linkages. And so as a result, we can metabolize starch, but not cellulose, only starch. And so if you continue on in your chemistry path and go on to biochemistry, you will spend a lot of time talking about carbohydrates. It's one of the ways that we get energy. It's super exciting, and the enzymes that cause these types of reactions. But we're starting our building blocks here, looking at the different mechanisms that help us get prepared for biochemistry. Well, this concludes chapter 9 for us. We will pick up in chapter 10, where we will start talking about synthesis.